In the light of fast development of cyber threats, the complexity of heterogeneous ICT ecosystems raise major security concerns. In this regard, Bieco provides a set of tools and methodologies for building trust with respect to malicious attacks that can endanger the safety of a system and of the ecosystem. More specifically, Bieco provides various mechanisms for malicious failure prediction and trust assurance, considering the design time and runtime phase of a system. These mechanisms are instrumented by an online framework that connects various methods and tools. Even though the approaches are general, for being more specific in explanations, we exemplify the execution of Bieco within a robotic use case. The Research Consortium, funded by the European Commission, through the Research and Innovation Programme, is composed of 11 partners, from 7 European countries: Portugal, Italy, Romania, Austria, Spain, Poland, and Germany. For the design time phase, we will start with the context establishment, continue to the risk identification step, further on the security testing and security assessment that result into the labeling phase. For runtime, we present the auditing setup, creation of digital twins, the finalization of the well-defined rules, followed by the execution of the auditing framework. The user interface provides access to both users and tool developers, in order to be able to define, control the status and interact with specific tools. Tools are defined in a similar fashion as microservices, with asynchronous access, multitasking and loose coupling. So, they are able to connect to the platform, receive and send data for specific jobs. We define jobs as a collection of steps that need to be executed in order to provide some results to the user. One or more tools can be defined in each step, so they can be executed either in parallel or sequentially. This accommodates both the runtime and design time methodologies, in an abstract, extendable and loosely coupled way. The Bieco platform has two main components, the UI and the orchestrator, components that cooperate and respond to user requests. Tools can be defined in the Tools section by tool developers. They can define different aspects, like endpoint, access tokens, inputs, and also enable or disable the tool. Services is the section that provides an overview of the connected tools and their state. This page is continuously refreshed in order to retrieve the latest statuses. If any of the used tools for a methodology is not online, the platform will not be able to execute a specific job. Different projects for a user are defined as jobs, since they can be executed by a user. Defining a job is easy, providing a name and description. Other information and settings will be defined as the project progresses. The job view has a direct connection with the UI and orchestrator via a WebSocket connection. Any failure in the Bieco platform will be immediately announced to the user. The job status can be assessed from the overview, along with the last execution timestamp. The history table provides useful information about the last execution of the job with relevant events and results. This table can be downloaded in CSV format, for offline use. The two methodologies, runtime and design time, have their own tabs, with specific interfaces for both. Interaction with the tool UIs can be done via specific buttons. Each methodology provides its own possible actions, steps and results. The job execution does not stop when closing the browser window. It is possible to close it and come back later for the results. The data collection tool, DCT, allows the assessment of a system's components in terms of security and trust, before they are added to the supply chain. It has a web interface and interacts with the other Bieco tools through a REST API. The tool contains public and internal data. The public data refers to products, vulnerabilities, exploits, and weaknesses. The desired information can be easily found using the DCT's search facilities. For example, we can search for the vendor Canonical, which is the developer of Ubuntu, and find all its products and their vulnerabilities. There are also searches for products, versions, vulnerabilities, and weaknesses. The DCT also serves for MUD files storage. The internal data in the DCT is collected from the use cases and it refers to their software components and bugs. By clicking on Open Resol Blockly, a silent authentication is performed, and the two main features of the tool, Profile and Model Designer, become visible. In Model Designer, it is now possible to see a part of the modeled use case system. Among other features, risk assessment allows to determine communication rules for the interfaces existing in the model. Selecting one of them, it is then possible to import the original MUD file from the data collection tool by simply inserting its ID. In the first tab, General, is shown the information automatically retrieved from the original MUD JSON, like the MUD system info. Then, in the Rules tab, additional data regarding the communication rules can be provided by the user. Similarly, information about application protocols can be added, as well as resources or keys. This amount of information that extends the MUD can be visualized and compared to the original MUD. Moreover, the user can identify weaknesses of a component's interface, for example retrieving them from the CWE catalog, and associate to that interface. With a similar approach, also vulnerabilities retrieved from CVE can be associated. Then, the user can perform a preliminary risk assessment of weaknesses and vulnerabilities by inserting severity and likelihood. The information about the threat analysis and risk assessment is also included in the extended MUD. The vulnerability forecasting tool can be used to evaluate the level of trust in the supply chain components. It uses neural network models to forecast the number of vulnerabilities and bugs that will be discovered in certain timeframes. The tool is currently under development, but there are already working models, which are related to use case 4. The first set of models are referring to the Ubuntu operating system. All the versions of Ubuntu and their number of vulnerabilities are shown here. The tool presents forecasts for the monthly vulnerabilities, and the averages for the next 2, 3 and 6 months. The information is presented both in numeric and graphic format. The second set of tools is related to the bugs of the robot operating system. Bugs can lead to weaknesses, which could be exploited and thus turn into vulnerabilities. For training our prediction models, we used the dataset provided by the Rosin project, which also has a GitHub repository. The dataset contains bugs and warnings, based on which we calculated cumulative warning levels, which are also used as inputs to our models. The forecasting models estimate the number of bugs for the next month, and the averages for the next 2, 3, and 6 months. Other prediction models will be added to the forecasting tool in the remaining months. The Bieco UI integrates the GraphWalker tool, which can be used by the user for model-based testing. In this tool, the user models the system at a high level as a state diagram. Nodes represent states, and arrows transitions. This is the model of the local planner component of the use case 4, necessary to generate 7 tests, for confidentiality, integrity, and availability. These tests check different aspects, such as the protection of the data, the updates, or the resistance against denial of service attacks. While in general, the tests will be binary, pass or fail, some tests will measure certain aspects, for example the maximum number of simultaneous connections, before the system crashes. The tests are labeled using the tag requirements, which will be used as a coverage condition, for the automated test generation. The user can export the model, and use it as input, for the test suite generator tool. This tool automatically generates 2 files. The first one is the JUnit test suite, with the 7 generated tests, and the second one is an interface called adapter, to link the high-level test operations with the real system. The adapter must be implemented by the user, to run the test suite over the real system, and obtain the test report. In this case, 5 tests fail, 1 test passes, and the non-binary test obtains a metric of 1 for the number of simultaneous connections. For a more complete testing report, the user can also find the fuzzing tool, a testing tool which identifies errors or unexpected requests. For its execution, it is required to upload the API specification under test to the Bieco platform, in the form of a Swagger file. Once it is uploaded, run the tool. When executing, a large number of requests are launched against the API under test, checking which of them can fail. This process may take time depending on the complexity of the analyzed API. Once the process ends, the tool generates 2 reports, one that is delivered to the Bieco platform to be used by other tools, and another for the user with the suspicious inputs that can affect the platform and their corresponding outputs. This part of the video is dedicated to Security Scorer. It is a tool provided to evaluate the security score of the analyzed system. The figure displayed right now is an overview of Bieco's security certification methodology, from Deliverables 7.2. In the model, the risk evaluation is based on the output of the risk identification phase. That's why in order to evaluate the risk, Security Scorer needs a system description, and output data from other tools. Deliverables 7.1 describes modeling of the system's security properties, by decomposing them on components and claims. In turn, claims can contain vulnerabilities and tests. There can be multiple system components and multiple tests per claim. Here's an example of what the output of the risk identification phase might look like. However, this theoretical description has to be passed to our tool, in a user-friendly way. That's why, for the modeling, a YAML file is used. Here's an example of such a file. It allows mapping specific tests to claims, and claims to system components. Other essential inputs for the security scorer are the outputs of the risk identification tools, such as the graph walker and the fuzzing tool. The XML file consists of the test suites, consisting of individual test cases. If any test case fails, necessary supporting information is passed inside the test case element as a failure or an error. The test cases with no data inside are considered as passed. Provided with metadata, YAML file and XML output files, the security scorer can be called by the API. The output of the security scorer is a set of scores, one per system's security property. They are presented as a spider chart in the Bieco user interface. Once the design phase has been completed, the runtime phase can start. It targets the monitoring of functional and non-functional properties during the execution. In particular, it involves the interaction between the system of systems, that is the controlled environment, and a new component or device, that is the system under auditing. In this demo, we will focus on setup and execution of one of the runtime phase components, that is the auditing framework. In particular, we will show the join interaction between its three main components that are the ontology manager, the monitoring engine, and the predictive simulation. The auditing activity starts with the selection of the auditing framework setup, that includes as first step, the pre-setup phase. During this step, Bieco provides the user the possibility to explore the classification and categorization of the different systems of systems, their devices and components. Indeed, through the interface, a list of different systems of systems is shown and the user can select the most suitable one. In this case, the autonomous navigation. Then, the list of relative devices is visualized, so that the user could select the target of the auditing stage. In this case, Robot Unit 1. Successively, the list of the components of the selected device is provided, so that the user can select the suitable one. In this case, Local Planner 1. At this point, the specific component skills are visualized: connectivity and movement. The user decides to select connectivity, because it is considered the most critical from the security point of view. The lists of the most suitable functional and non-functional properties are then selected and visualized. These are presented as high-level specifications and called abstract rules. They are divided into two groups: standard and pure predictive. The standard rules are non-functional properties that can be assessed through monitor. For instance, the user can select the maximum number of established simultaneous connections. It targets the mutual interaction between the local planner 1 and the autonomous navigation, that is the controlled environment. In this case, rule boundaries can be established, either using data collected during design time phase, or provided by the user. They remain valid for all runtime execution. The pure predictive rules are instead functional properties that can be predicted through digital twin. For instance, the expected communication pattern through an ordered list of message types. It focuses on the specific behavior of the local planner 1 and requires that the digital twin predicts and forecasts to monitor the specific messages order. If not available already, as a final step, the user needs to insert the boundaries for the selected abstract rules. In this case, the maximum number is set to 1. This concludes the pre-setup phase. Then, a set of useful downloadable artifacts is proposed to the user. These include a set of guidelines for using the DSL language and derive the digital twin, a jar of the executable probe, and a set of guidelines useful for instrumenting the code. At this point, the control goes back to the Bieco GUI. At this stage, the user works offline for preparing the required digital twin and instrumenting the local planner 1 and the controlled environment and the digital twin itself with suitable probes. In this short video, the probe inserted into local planner 1 is visualized. The development of the models for the digital twins is guided by a domain-specific language, also known as DSL. The DSL is based on a grammar that contains rules that guide the development process at the user side. These rules specify the way in which the models shall be structured. For example, the grammar rule for entity enables definition of structures for holding behavior specification. With the support of the Xtext framework, when code is written according to the imposed pattern, corresponding source code is being generated. In practice, the user, who is also the developer of a software component to be integrated in a supply chain, uses the domain-specific language to specify the behavior of this component. This implies that with every new software component that is introduced in a supply chain, corresponding executable models need to be provided as well. When fed with real-time data, these models become digital twins. For creating the executable models, in a Java development environment that integrates Xtext, the user creates within a project a file with the extension that refers to the language. Automatically, the pop-out menu enables usage of pre-defined structure, like package entities. The user then starts to write the behavior by structuring it accordingly. In the running example, we define the behavior of the local planner that guides the navigation of the robot. With every build, the code for the executable models is generated. In the running example, the navigation module interacts with other entities. This interaction needs to be specified in the behavioral description. Interactions are captured in dedicated constructs that enable gathering information that is being exchanged. This information is later on encapsulated within specific events that are monitored for conformity with the execution in the real world or controlled environment. Decision events will be those events that cross the architectural boundaries of an internal component, whereas normal events describe normal input-output interaction with components within the same architectural structure. Fast forward, all behavior is being declared and corresponding models are created. These models are then packed as jars and executed in a predictive simulation environment. Now, the auditing framework setup needs to be completed with the last step, that is the finish pre-setup. In this case, the user first needs to upload the prepared digital twin. Then, the user needs to finalize the well-defined rule by providing the identifiers of the probes injected. In this case, for the rule named maximum number of established simultaneous connections, the user inserts SUA probe. For the pure predictive rule named expected communication pattern through an ordered list of message types, the user inserts DT probe. Here we see the controlled environment for this demonstration. It consists in a Capella sim simulation, representing the multi-robot navigation scenario for intralogistics, as depicted in the overlay. The system under audit is part of the robot on the left, with probes being injected into the local planner component for the navigation. Under normal conditions, both robots should follow the computed path, while avoiding environmental objects and each other. With the button Start Auditing Framework, a start command is sent by the orchestrator to the auditing framework, so that the auditing framework can start. Monitoring engine goes from online state to running. It raises up the complex event processor and receives the rules defined in the setup phase. Then, it compiles the rules into meta rules and instantiated rules. At this point, the monitoring starts listening to the events sent by the probes on a dedicated channel. Here is shown the sewer probe injected in the local planner 1 that sends events related to velocity and score. In parallel, listening from the same channel, the predictive simulation receives the events useful for fed abstract models. These are executed at a faster rate than the controlled environment, and can therefore provide predictions about trusted behavior. Considering the rule called expected communication pattern through an ordered list of message types, here we show the DT probe injected into the digital twin. It includes DT forecast event, containing a digital twin prediction in terms of a sequence of velocity and score events. Using the data of the DT forecast event, the monitor instantiates the meta rule into a new rule, and injects it into the complex event processor. The time frame validity of the new rule will be set to 5 seconds, as established in the DT forecast event. On the monitoring side, the monitor continuously receives the sewer probe events, containing score, velocity and connection status, and checks the set of instantiated rules. For the sake of this demo, a malicious code attack has been simulated. For this purpose, the malicious code injection is performed through the UI provided with the controlled environment. Due to this, the number of connections between the local planner 1 and the global planner increases, as shown in the UI. On the monitoring side, this causes the violation of the maximum number of established simultaneous connections rule, as shown in this video. In this case, a notification is sent to the Bieco platform, and the auditing framework stops immediately. Once this untrusted behavior is detected by Bieco's auditing framework, the dynamic configuration of the system under test can be triggered. Here this is once again simulated via the controlled environment UI, returning the system into a safe and trusted condition.